Thank you for watching my presentation. The title is Development of Deep Learning Library for AArch64 CPU. My name is Kentaro Kawakami. I'm working for Fujitsu, Japan. I've engaged in research and development of AI software for Arm HPC, especially for the supercomputer Fugaku for the last 2 years. This is the table of contents of my presentation. Firstly, I'll explain background and motivation of porting oneDNN for AArch64. oneDNN is one of the deep learning processing library which is developed by Intel. Secondly, calculation kernel generation of oneDNN is explained. This is a key point of oneDNN. And then I'll show you how to develop oneDNN for ARM architecture. I'll also introduce a binary translator to accelerate development. And finally, I'll summarize my talk. The supercomputer Fugaku was put in service in March of this year. Fugaku is 3 consecutive top 500 winner for the last 2 years. Fujitsu A64 is used as the CPU of Fugaku, which complies with the Armv8-A architecture and supports scalable vector extension instructions for HPC. I am developing software to accelerate deep learning processing in Arm HPC, especially for Fugaku and its derivative systems. This figure shows the software stack structure of the deep learning processing. The stack is roughly divided in 2 levels, the front-end framework software and the back-end library software. TensorFlow and PyTorch are the major frameworks. The frameworks are written in Python and C++, and the source code is available as OSS. They are implemented in a hardware-independent manner so that we can compile and use them for A64FX. The library software provides calculation kernels. Those are repeatedly executed in the deep learning processing. Since the calculation kernel accounts for most of the computation load in the deep learning processing, the optimized libraries are provided for each hardware to reduce the processing time. As you know, cuDNN for NVIDIA GPU and oneDNN for Intel CPU are representative libraries. There was no deep learning library for ARM architecture, so we had to develop a new one. We choose to implement a library for A64FX based on oneDNN because it would take a lot of development time to create a completely new library. This slide shows the advantage of using oneDNN as the porting target. oneDNN is an OSS and written in the standard C++, so we can access the source code and build it for A64FX. The major deep learning frameworks supports oneDNN, so if we can port it to A64FX, deep learning applications using these frameworks can easily run on Fugaku as well. In addition, oneDNN is implemented to accelerate deep learning processing on CPU-based computers. oneDNN implements multi-thread processing and input-output data reordering to increase the computation efficiency, and these functions can be used for A64FX as well. This section explains the calculation kernel generation of oneDNN. oneDNN provides the computation functions of convolution, batch normalization, L-twice, pooling, summation, and so on. They are commonly used in the deep learning processing. The optimized kernels are provided for AVX512, AVX2, AVX, and SSE 4.2. A calculation kernel is selected according to the instruction sets supported by the computer which you use. This slide describes the calculation kernel generation. oneDNN uses Xbyak to generate the calculation kernels. Xbyak is a just-in-time assembler for Intel CPU. It's an open source software written in the standard C++. Xbyak provides the functions to write the machine code of a specified Intel CPU instruction to memory. By using Xbyak to write out a machine code sequence, we can generate an entire subroutine that performs the processing we want to do. oneDNN generates the optimal subroutine considering the runtime parameters and the available instruction set. The kernel generation is one of the key features of oneDNN. Now let's move on to the actual development of oneDNN to A64FX. oneDNN development for A64FX means implementing the calculation kernel generation for SVE512. Except for the calculation kernel generation, such as the interfaces to frameworks, multi-thread control, data order handling, and so on, the source code can be used as is for A64FX because they are implemented in the standard C++ and independent from the hardware architecture. In order to realize the calculation kernel generation for ARM CPU, a JIT assembler for ARM CPU is required. We have developed the JIT assembler Xbyak AArch64, which was presented at the last Linux Virtual Connect. The source code is disclosed on the GitHub. Xbyak AArch64 can generate the Scala, Neon, and SVE instructions up to Armv8-A version 8.2 instruction set. The version 8.3 and above are currently under development. We confirmed Xbyak AArch64 works with A64FX, Apple M1, Raspberry Pi 3, and QM. It may also work on other ARM systems such as Android, Jetson Nano, and so on. This page shows oneDNN source code tree. The source code of the kernel generation for Intel CPU is placed in the directory named x64. The implementation is in a separate file for each instruction set. For example, the files whose name starts with JIT AVX512 contains the implementation for AVX512. The figure below shows the code example written in Xbyak. VPMoveSDB is an AVX512 instruction, and this example writes 16 VPMoveSDB instructions to memory. We must be aware of instructions and registers for writing source code using Xbyak. oneDNN includes implementations for AVX512, AVX2, AVX, and SSE 4.1. And the implementation for AVX512 generates the fastest kernels, so we used it as the baseline source code for A64FX. The table shows a comparison of the CPU architecture of AVX512 and A64FX. Fortunately, the assembly size and the number of assembly registers are the same for these two architectures. And both CPUs support assembly instructions with mask operations. The size and the number of assembly registers are the same for AVX512 and A64FX. There is no need to run out of registers when rewriting an AVX512 implementation for SVE512. Therefore, we can simply replace AVX512 instruction with SVE instruction that do the same operation. The example above is such a simple example. VPADDD instruction is a assembly addition of 32-bit integers for AVX512. In A64FX, assembly addition of 32-bit integer is add instruction, so it can be written as shown on the right example. However, it gets complicated when there is no counterpart instruction in SVE. VPMove-SDB is integer conversion instruction for AVX512. SVE has no single instruction corresponding to VPMove-SDB. In this case, we have to rewrite it with multiple instructions to achieve the same operation. The source code of oneDNN is more than hundreds of thousands of lines. It's very difficult to extract the code using Xbyak and replace it with ARM instructions. We have developed a method to simplify the rewriting work. In order to accelerate the development of oneDNN for A64FX, we have developed a binary translator that can generate calculation kernel for A64FX by running the implementation for AVX512. We call this binary translator a Xbyak translator AArch64. The original implementation for AVX512 generates machine code for Intel CPU by using Xbyak. The translator uses the disassembler to extract the instruction mnemonic and operand information from the machine code of Intel CPU. And the translation table contains the correspondence between Intel CPU instruction and ARM CPU instructions. Using this table, Xbyak AArch64 functions are called to generate ARM machine code, which performs the same operation as the instruction generated by Xbyak. By repeating these processes, the entire calculation kernel can be converted for A64FX. Next, I'll explain the four components of the translator in turn. Xbyak used in the translator has been slightly modified from the original. For example, Xbyak has been modified to kick in the disassembler process after generating Intel machine code. This change is very simple. Just a single step was added to call the disassembler. And for the branch instructions, Xbyak has been changed to call Xbyak AArch64 functions to directly generate ARM branch instructions. This change is also easy because Xbyak and Xbyak AArch64 are compatible in their implementation of branch level handling. The interface of Xbyak is identical to the original Xbyak. As an alternative to the original Xbyak, the translator can be directly inserted into oneDNN. we implemented the disassembler part using Intel XED. XED is an encoding and decoding library for Intel instructions, and its source code is available as OSS. XED provides the functions to extract the instruction mnemonics, operand types, and operand values from Intel machine code. Xbyak AArch64 has not been changed at all from that was originally developed. The translation table is the most difficult part of the translator development. oneDNN generates more than 200 types of the Intel instruction at runtime. Each instruction has several tens of minor operand variations. Therefore, the translation table must contain the correspondence between several thousand Intel instruction variations and ARM instructions in total. The translation table is implemented as a separate header file for each Intel instruction to be converted. The current version of the translator has conversion tables for 221 different Intel mnemonics. Each header file is generated from an Excel file. This table defines the conversion of VPADDD instruction. VPADDD performs 32-bit integer addition of 521-bit SIMD, and it has 9 variations depending on the combination of operands. This table expresses the translation rule for the 9 variations. Column C, D, and E contain the information necessary to distinguish between the 9 variations. For example, in the third operand is register, no mask and no memory operand are specified. We can say the combination is Z register, and Z register. The columns H through V describe the specific ARM instruction sequence to be output for each variation of Intel instruction. The A64 structure contains the detailed information of the operand extracted by the disassembler. Using the disassembled information and Xbyak AArch64 functions, we can describe how to generate ARM instructions correspond to VPADDD instruction. The column F shows the code generated by this table. The code is written in VPADDD.h file. Now, I explained oneDNN for A64 using the translator. If oneDNN is upgraded by Intel, we can run it for A64 by replacing Xbyak in the latest oneDNN with Xbyak translator AArch64. So we can easily provide the latest oneDNN for A64 users. This slide explains some limitations of the translator. Due to the time constraint, I will skip this slide. This page shows the other constraint of the translator. If there is a logical instruction before the conditional branch instruction in the original implementation, we have to insert a compare instruction manually. This is because Intel's logic instructions always update the conditional branch flag, while the ARM's logic instructions do not change the flag. So a compare instruction is required to correctly execute a conditional branch instruction. All of the software presented today is available on GitHub. PyTorch and TensorFlow are also available for use with oneDNN for A64FX. The materials of Xbyak AArch64, which I presented at the last Linear Virtual Connect, is here. Bug reports, requests, and contributions are very welcome. The translator has been developed for 512-bit SVE. You may be interested to see if it works with SVE 256 or 128. I haven't checked it properly, but I believe it works. Since the LVX2 instruction is a 256-bit SIMD, it seems to match SVE 256. Actually, I tried to run the LVX2 implementation on SVE 256 environment. The test patterns for convolution kernel completely passed. Similarly, I believe that the implementation for LVX can be used for SVE 128. But I think some instruction conversion rule may be missing. The implementation for LVX2 and LVX may use instructions that are not used for LVX 512. In this case, it's necessary to add an Excel file that defines the translation rule. This slide shows a translation result example of an LVX2 instruction. When VPADDD instruction with YMM register is executed on an LVX512 CPU, the upper 256 bits of the DMM register are cleared to 0. The translator generates a move instruction that clears the upper 256 bits to 0 to achieve the same behavior when run on the SVE 512 CPU. So if translator is run on the SVE 256 CPU, the move instruction has no effect and it is redundant for SVE 256 CPU. In order to use the translator to generate higher performance computation kernels, it may be necessary to improve the translator so that it does not output this move instruction. Let me summarize my presentation. To achieve high-speed deep learning processing on HPC systems with A64FX, we have developed the deep learning software stack. oneDNN, a de facto deep learning processing library for CPU, is ported and optimized for A64FX. Since oneDNN is implemented at the instruction level using Z-assembler, it takes a lot of time to port it to A64FX. To accelerate development, we implemented the binary translator, which enables us to divert the implementation time of oneDNN for A64FX. I hope this software will be useful for many ARM users. We would like to express my sincere gratitude to Mr. Shigeo Mizunari of Cyborgs Labs, the developer of Xbyak. Mr. Mizunari provided us a lot of useful advice, and he helped us with the development of Xbyak AArch64 and the translator. Thank you for watching my presentation.